Okay, so welcome to section 11.3, which is geometric sequences. Okay, so definition. So a geometric sequence is a sequence. I know. I need a thesaurus. Is a sequence which how do I want to state this? Which increases by a fixed ratio as opposed to distance, a fixed ratio, not ratio, ratio R between subsequent terms. So between subsequent terms. So that is, pardon me, of course, I'm allergic to doing work. So for example, or that is rather, id est a sub n will be the first term a sub 1. Then the second term will be r times a sub 1. And then r times the previous term, r times the previous term, etc. Ad infinitum if it's an infinite sequence. Okay, so let's note we have that a1 is really a1 times r to the 0. And let me be explicit here with my subscripts and my coloring. We have that a sub 2 can be thought of as a1 times r to the first. A sub 3 can be thought of as a1 times r to the second. So in general, we have that a sub n will be a1, the first term, times r to the n minus 1. Okay, so for example, so let's find the common ratio. So find both the common ratio r and first term a sub 1 for the following geometric sequences. Having geometric sequences. Okay, so number 1, let's say we have 2, 4, 8, 16, 32, etc. Okay, so I claim that a sub 1 is 2, that a sub 2 is 4, that a sub 3 is 8, that a sub 4, and this should be sufficient, a sub 4 is 16, etc. So what I want to do is I want to find the common ratio. Now, in order to do this, we have to be careful. What we need to do is the next term over the previous term. So 4 divided by 2 is 2. Similarly here, the next term is 8. The previous term is 4. So this gives us a common ratio of 2. The next term in this scenario is 16 divided by the previous term is 8. So once again, we get 2. So I claim that the common ratio R is 2, and we've listed the first term as 2 as well. Okay, so number 2. Let's say we have the sequence, what shall we do? 12, 36, 108, something like so. And that's all I'm going to give. So A sub 1, pardon me, is 12. A sub 2 is going to be 36. And finally, we're only given A sub 3, which is 108. Okay, so let's see. The ratio of subsequent terms in this first case is 36 divided by 12, which is 3. In the second case, it's 108 divided by 36. Okay, well, 108 divided by 36. Well, let's see, 36 times 3 is really 30 times 3, which is 90. And 6 times 3, which is 18, so that works. It is 3, so check mark. So we have that the common ratio here is 3. So we're okay. So third time's a charm. Let's say we have the sequence 375, 75, 15, 3, etc. So now we have that A sub 1 is 375. We have that A sub 2, the second term of the sequence, is 75. We have that A sub 3, oh, come on. Ugh, okay, yeah. A sub 3 is going to be, third term of the sequence is 15. We have that A sub 4, oops, wrong color. A sub 4, the fourth term of the sequence is 3. Okay, so let's go ahead and find the ratio of subsequent terms. So I claim that 75 over 375. Well, what's that going to be? So how many times does 75 go into 375? Well, 75 cents times 2 would be $1.50, so that's 150. If I add another 75 cents to $1.50, that would give me $2.25. If I add another 75 cents, that's 300. So where am I so far? That's 4 times 75. So I claim that this reduces to 1 over 5. And let's see if that's true. Maybe this one will be easier to calculate. We have 15 over 75. Well, I know that 1 plus 5 is 6, so 3 goes into that. 7 plus 5 is 12, so 3 goes into that. So if I were to divide by 3, I'd have 5 over 25, and 5 over 25 reduces to 1/5. Yes, okay, it works. This one, it should be our easiest one to calculate. 3 into 15 is indeed 1 over 5. So we do have the correct ratio, 1/5. So our common ratio in this case is 1 over 5. Common ratio is 1/5. Okay, so let's consider, I don't have enough room. It's only digital, so let's consider, I don't know why I'm worried about saving digital paper, but I still am. So let's consider that we have A sub n is A1 r to the n minus first, according to this, right? Okay, so I'm going to do a trick. I'm going to say this is A1 r to the n minus 1, then I'm going to subtract 1 but add it right back in. So technically I'm adding 0. So this is A sub 1 r to the n. Now I'm going to group these two together, so n minus 2 times r to the first. And now I'll bring that r to the first in front, times a1 r to the n minus 2. So by definition, a1 r to the n minus 2 will be a sub n minus 1, because the exponent on r is 1 less than the subscript on a. So what do we have here? We have the recursive definitions theorem. Nope, it's not going to autocorrect. Thank you. So the recursive form of a geometric sequence with first term A and common ratio R is given by A sub n is R times A sub n minus 1. So that is our recursive definition. So, for example, so find the first 5 terms. So find the first 5 terms of the geometric sequences. And this is where we're going to differ a bit. Beginning with n, so beginning with n equals to 0. So now I'm going to start counting at 0 instead of at 1. This is common for geometric sequences. So number 1. Let's say we have that a sub n is defined as 5 times the quantity 2 to the n. Okay, so I claim that a sub 1 is going to be 5 times 2 to the first power, which is 10. I claim that a sub 2 is going to be 5 times 2 to the second power, so 4 times 5 is 20. A sub 3, I claim, will be 5 times 2 to the third power, or 8. 8 times 5 is 40. A sub 4, I claim, will be 5 times 2 to the fourth. Remember, the exponent is only on 2. 2 to the fourth, of course, is 16. 16 times 5. 10 times 5 is 50. 6 times 5 is 80. So 50, sorry, oh my goodness, I'm giving the answer. Okay, so 16 times 5. 5 times 10 is 50. 6 times 5 is 30. 50 plus 30 is 80. Should not give away the answer beforehand. Okay, so a sub 5, the final term. Oh my goodness, I just said to start with 0, and I didn't include 0. Okay, well, I'm going to have to go back because I didn't even read my own directions. 2 to the 5th. Okay, so 2 to the 5th is 32. 5 times 3 would be, or 5 times 30 would be 150. And 5 times 2 is 10, so that's going to be 160. But I'm going to do something that I know is going to upset you because I'm sure you didn't use pencil. Like I told you to. So there we go. It's almost the end of the semester. And now I make a really big mistake that you have to rewrite. Or at least just put it somewhere. So 2 to the 0. 2 to the 0 is 1. So we just get 5. And notice we've just been doubling each time. 5, 10, 20, 40, 80, 160. Because we have R, our common ratio is 2. So we double each time. Okay, so number 2. Let's say we have that a sub n is given as 1875 times the quantity 1/5 to the n. Okay, so now let's see if I can start with the correct subscript now. So a sub 0 will be 1875. Actually, let me do that in purple. So 1875 times 1/5 to the 0, meaning 1. So it's just 1875. Notice I'm using equal signs between each term. A sub 1 is going to be 1875 times 1/5 to the 1st. Okay, so now I'm basically dividing 1875 by 5. 5 goes into 18 3 times with 3 left over. 5 goes into 37 7 times with 2 left over. And 5 goes into 25 5 times. So a sub 2 is going to be 1875. It's supposed to be an 8. 1875. Now we have 1/5 quantity squared, which means I'll be dividing by 25. Okay, well, 25 into 187. I know that 25 goes into 175, but how many times? Well, I claim that it goes into 100 4 times, so therefore it goes into 175 7 times. With how much left over? Well, 75 to 87 is 12, and 5 goes into 125 25 times. Wait, 5, oh my goodness. 25 goes into 125 5 times. That's what I'm trying to say. I guess I should show my work instead of just trying to say my work, but you're beyond algebra now, or you're beyond arithmetic, so we're doing it in our heads. So now we have 1/5 to the 3rd power. Okay, so now I'm dividing 1875 by 125. Okay, so I claim that that's going to be, well, what is it going to be? Can anyone tell me? What have I done? I've been dividing each term that preceded it by 5. So what's 75 divided by 5? Well, I claim that, I'm, holy free holy, what is wrong with me? Yes, so I'm dividing the previous term by 5. So 5 goes into 7 once with 2 left over, and into 25 5 times. Okay, let's see if I can do this. A sub 4 will be 1875 divided by 5 to the 4th power, or multiplied by 1/5 to the 4th. So basically I'm just going to divide the previous term by 5. Look at that. I get 3. And we can stop there, because technically that's 5 terms if I count it from 0. Okay, why would I not go to a sub 5? Oh, no. Because what would happen when I go to a sub 5? What am I going to introduce? I'm going to divide the term right above it by 5. So I'm actually going to introduce fractions at that point. And nobody likes fractions, so let's continue. So number 3, let's say we have that a sub n is going to be fraction 4/3 to the nth. Oh boy, what did I just say? I'm a mean person. Okay, so let's say we have that a sub 1. Sorry, we're starting with 0. Why do I keep on forgetting that? Okay. So we have quantity 4/3 to the 0 power. Anything to the 0 power, of course, is 1 besides 0 itself, but you'll worry about that next semester. So a sub 1 is going to be 4/3 to the 1st power, which of course is just 4/3. A sub 2 is going to be 4/3 to the 2nd power. So what do I get? 16 over 9. A sub 3 is going to be 4/3 to the 3rd power. So what do I get? I get 64 over 27. A sub 4 is going to be 4/3 to the 4th power, so 4 to the 4th. 64 times 4, that's 256, right? And 3 times 27 will be 81. And last but not least, A sub 5 is 4/3 to the 5th power. So all I'm going to do is I'm going to multiply the previous guy by 4. So 200 times 4 would be 800. But 50 times 4 is another 200, so that's 1,000. And 6 times 4 is 24. So 1024. 81 times 3 is 243, I believe. Yeah. Okay, so there we are. So let's recall. That A sub n is equal to A1 times R to the n minus 1 in explicit form, right? Meaning not recursive, explicit form. Okay. So for example, so let's find the explicit form. So find the explicit form of the following geometric sequences. Okay, so number 1, let's say we have -1, comma 4, comma -16, comma 64, comma -256, comma ... Okay, so I know that A sub 1 is -1. Now I just need to find the common ratio, right? Well, A sub 2, why did I use purple as my subscript? So A sub 2 is going to be +4. A sub 3 is going to be -16. And you know what? That should be enough. So to find my common ratio, I'm going to do next term divided by previous term. So that's going to give me -4. Is that indeed my common ratio? Well, let's see. -16 divided by 4 is -4. Okay, so my common ratio is -4. Okay, so what this means is that A sub n is going to be A1, which I claim as -1, times the quantity common ratio, -4, to the n minus first. Okay, so if n is 1, we get -1. If n is 2, we get a +4. Yeah, okay, that works. There we are. Okay, so number 2, let's say we have the sequence 2/3, then 5/6, then 25/24, then 125, what do I want to do? 96, something like that. Okay. So what do we have here? We have that A sub 1 is 2/3. We have that A sub 2 is 5/6. We have that A sub 3 is 25/24, and that should be enough. So if I take the ratio of subsequent terms, this is going to be 5/6 times the reciprocal of 2/3, which is 3/2. So 3 goes into 6 twice, leaving me with 5/4. So hopefully that's our common ratio. So this is now going to be 25/24 times the reciprocal 6/5. Okay, 5 goes into 25 5 times, and 6 goes into 24 4 times, so 5/4. Yeah, very good. It works. So we have that the common ratio here is 5/4. So I claim that our A sub n in pink will be A1, which is 2/3, times the quantity R, common ratio, 5/4. I don't know why I didn't just put R in green. That would have made more sense, wouldn't it? Let me do that. What is wrong with me? I don't know. Okay, so let's put this in green. I don't know if that's the right green. I think that's the wrong green. Yeah, that's a better green. Okay, so here the common ratio is going to be 5/4 to the n minus first. Okay, third time's a charm, so number 1, 2, 3. Let's say we have 0.1, 0.01, 0.001, etc. Okay, so we have now that A sub 1 is 0.1. We have that A sub 2 is 0.01. We have that A sub 3 is 0.001. But before we start our common ratio, this is 1/1 with 1 0, because there's 1 0 preceding the decimal. And this is 1/1 with 2 zeros, because including the 0 that precedes the decimal, it's 100 backwards. This is 1/1000. For the same reason, read backwards, it's 1,000. Okay, so now let's look at our common ratios, namely 1/100 times the reciprocal, 10/1, gives us 1/10. Okay, now we have 1/1000 times the reciprocal, 100/1, which gives us 1/10. So I claim the common ratio is 1/10. So therefore, A sub n is going to be the first term, which is really 1/10. And we're going to have 1/10 to the n minus first. Okay. And you might be asking, why didn't I start with 0? Well, that's a good question, but had I started with 0, 0 minus 1 makes no sense, because the exponent needs to be either 0 or positive. So welcome to math. Okay, so now I'm going to veer off from geometric sequences and go back to general sequences. So theorem, let me get a different purple. So theorem, so let's let, actually I might write it like this. Let's let C1 and C2 be real numbers. Then the roots R1 and, don't need a comma there, R1 and R2 of, how do I want to say this, R squared minus C1 times R minus C2 equals to 0 can be used to translate the recursive sequence A sub n is equal to, and here's where C1 A sub n minus 1 plus C2 A sub n minus 2 into not and, into explicit form. Form a sub n is equal to alpha times r1 to the n plus beta times r sub 2 to the n, where alpha and beta are some real numbers. Okay, and of course, n is an integer, usually positive or 0. Okay, so that is, i.e., given a sub n is equal to c1 a sub n minus 1 plus c2 a sub n minus 2. What color should I use? Solve r squared minus c1 times r, not minus, what am I saying, plus c2 equals to 0. Then a sub n will be alpha r1 to the n plus beta r sub 2 to the n. Solve a naught equals to alpha plus beta, a1 equals to alpha r1 plus beta r1 r2 as a system. So these are the steps we're going to take. Maybe I should have put nope, I still didn't do it right. Okay. So these are the steps. So given, so this is step 1, then we have step 2, then we have step 3, we have step 4. These are the steps to rewrite a recursive formula in explicit form. So let's see this. So for example, so rewrite the sequence 0, 1, 1, 2, 3, 5, 8. Given recursively as a sub n is equal to a sub n minus 1 plus a sub n minus 2 in explicit form. Okay, so step 1. We know that a sub n is equal to, I claim that this is 1 times a sub n minus 1 plus 1 times a sub n minus 2. So what that means is that c1 is equal to 1 and c2 is equal to 1. No, I did do it. Okay, sorry. Oh my goodness. No. Okay, got it. Just making sure I got that. These are minus. I was right. Okay, sorry. I'm like, it's not going to work out. Why is it not going to work out? Because I was right the first time. Sorry, these were minus. I should have just looked right up there. Okay. Yeah. Sorry, I should stop doing stuff in my head. Okay. So we've got C1 and C2. That's good. So now we can consider our formula r squared minus C1, which is going to be 1, times R, minus C2, which is also 1. We're going to set that to 0. Okay, so that's what we need to solve. And maybe I'm not going to use orange. It's too distracting. What color should I use? Pink? Pink is good. Okay. So I claim, using the quadratic no, oh my goodness, that this is a quadratic, so we do negative b, so minus a negative 1, plus or minus the square root of b squared, so negative 1 quantity squared, minus 4 times a, which in this case is 1, times c, which in this case is negative 1 in green. Actually, I should have done that parenthesis in green as well. Okay, there we go. This is underneath the radical. This is all over 2 times a, which of course is just 1. Okay, so we get that r is equal to 1 plus or minus the square root of 1 plus 4 is 5, all over 2. So we have that r1, where am I? So r sub 1 is equal to 1 plus the square root of 5 all over 2, and r sub 2 is equal to 1 minus the square root of 5 all over 2. So those are the roots, r1 and r2, of that quadratic formula. So where do I want to put them? Maybe I'll put them over here. I'll keep them over here. And then I will put a bracket around them. Okay, so this implies that these are our roots. Okay, so now what do I do? Now I need to set up that a sub n is some alpha times the first root to the n plus some beta times the second root to the n. Okay, so let's do that. So I claim that a sub n is going to be some alpha times the first root which is 1 plus root 5 all over 2 to the n plus some beta. What color should I use for that? I guess I'll use green. Some beta times the second root, which is 1 minus root 5 all over 2. Okay, having issues here clearly, to the n. Okay, so we've got that, and now we go back to what is given. What are a sub 0 and a sub 1? Well, I was given the first 2 terms of the sequence in this explicit form. So I know that a sub 0, which is going to be alpha times this big quantity here, copy, paste, to the 0, plus beta times this other big quantity to the 0, well, what is that when simplified? This is actually alpha times 1 plus beta times 1. And the first term of the sequence was given as 0. All that for nothing, right? 0. A sub 1 is going to be alpha times this big ugly thing here, this pink fraction, R1, to the first power plus beta times this big fraction here to the first power, which unfortunately is just what it is. So I'm just going to keep it the same way, I suppose. So alpha times the quantity 1 plus root 5 all over 2 plus beta times the quantity 1 minus root 5 all over 2 is equal to, what was A1, the second term? It was 1. Okay, so 1. So what I have now is a system. What color should I use? I'm going to use yellow. This system here, I have 2 equations and 2 unknowns. So I can solve this for alpha and beta, because everything else is known. Okay, so let's solve that system there. Well, I claim the first line says that alpha is negative beta, or beta is negative alpha, however you want to state it. Alpha is the negative of beta, and vice versa. If that's true, then I can look at the second line here, copy and paste, and I can say, okay, well, this is equivalent to saying that alpha times 1 plus root 5 minus alpha, because beta is the negative of alpha, times 1 minus root 5. Yeah, I guess I'll say all over 2. What the heck? All of this over 2 is equal to 1. Okay, so the first thing I'm going to do, well, technically the second, let's go ahead and cross multiply by 2. So let's get rid of the denominator. Let's multiply this whole fraction through by 2. So distributing, I'm going to have a positive alpha here and a negative alpha here, so those are going to reduce. Then I'll have root 5 alpha, or alpha root 5. I don't like that root 5, sorry. Let me draw that a bit better. Alpha times root 5 minus a negative alpha times root 5 is equal to 2, right? Okay, well, how many alpha root 5s do I have on the left? I have 2 alpha root 5s, right? That's equal to 2. So what am I solving for here? I'm solving for alpha. Okay, well, I claim that alpha, therefore, is going to be 1 over root 5. Agreed? Because if I divide both sides, let me just go ahead and divide both sides by 2 root 5. So 2 root 5, 2 root 5. I get that alpha is equal to 1 over the square root of 5, which implies that beta is negative 1 over the square root of 5. Okay, Okay, so therefore, our a sub n, actually I can just copy it and paste it. Where was our a sub n? It's right here. This big guy right here. Copy and paste. Can now be written as a sub n is going to be 1 over the square root of 5 times the quantity 1 plus root 5. You know what? I'm trying to make this look nice, but failing. So 1 plus root 5 all over 2 raised to the nth. And then we'll have minus 1 over the square root of 5 times the quantity 1 minus the square root of 5 all over 2 raised to the n. And there we go. That is the explicit form of this sequence. Now, why would I do this strange, really complex sequence? Well, this is a very special sequence. This is called the Fibonacci sequence. So, definition. The Fibonacci sequence. Fibonacci sequence is given recursively by, and there's actual capital F sub n. Is capital F sub n minus 1 plus capital F sub n minus 2, where F sub 0 is 0 and F sub 1 is 1. So that is, it is the sum, or not it, let's say each term, that sounds better. So each term is the sum of the previous two terms. But look at how crazy complicated that is. If only there was an easier way. Well, there is actually. But how long has this taken so far? Well, I can just say it as a note. One plus the square root of 5 all over 2 is equal to phi, the golden ratio. This is a very special number. And notice we have the golden ratio and tau, which is related to the golden ratio, in the calculations for the explicit value of phi. So let's consider the following. So if I have phi, I know that that's just 1 plus the square root of 5 all over 2. But let's say we have phi squared. Well, that's going to be quantity 1 plus the square root of 5 all over 2 squared, right? Okay, so expanding the binomial, we'll have 1 plus 2 times the square root of 5 plus 5 all over 4. So this means we have 6 plus 2 root 5 all over 4. Well, there's a 2 common to each term. So this is 3 plus root 5 all over 2. All over 2. Okay. Well, I claim that this is, I should have given myself more room. This down here. So I claim that this is, I can write this as 2 over 2 plus 1 plus root 5 over 2. Agreed? And when I do that, what do I get? I get that this is equal to 1 plus phi. So now the hard part's over. You're saying, how is that possible? Well, let's say phi cubed, I claim, can now be written as phi times phi squared. So that's just going to be phi times 1 plus phi. So now my life is easy. Distributing, that's phi plus phi squared. And I know that phi squared is 1 plus phi. So this is going to be 1 plus phi is 2 phi. Okay, what about phi to the 4th power? Well, once again, it's just going to be phi times phi cubed. So this is just going to be phi times the quantity 1 plus 2 phi, or phi plus 2 phi squared. So I'm doing twice this, so that's 2 plus 2 phi, plus 1 phi will be 2 plus 2 phi, and 1 phi is 3 phis. Okay, phi to the 5th. Why am I doing all of this? Is going to be phi times phi to the 4th. There must be a reason. And this is going to be phi times 2 plus 3 phi. Okay, so that's 2 phi plus 3 phi squared. Okay, so 3 phi squared. Well, if I take 3 times 1 plus phi, that's 3 plus 3 phi. 3 phi plus 2 phi is 5 phi. So 3 plus 5 phi. Look at these numbers. So what do I have so far? I have that phi is 1 times phi plus 0. I have that phi squared is 1 times phi plus 1. I have that phi cubed is 2 times phi plus 1. 1 in orange. I have that phi to the 4th is 3 times phi plus 2. Interesting. I have that, actually let me move this up. I have that phi to the 5th is 5 times phi plus 3. So let's look at these things. What do we have here? We have the sequence of coefficients of phi, 1, 1, 2, 3, 5. Coefficients. Of phi. Then we have the constant coefficients, 0, 1, 1, 2, 3. Constant coefficients. But what are these? This is this sequence. These are the Fibonacci numbers. In fact, I claim that for every power on n, I claim that phi to the n power is going to be Fibonacci number n, right? Because Fibonacci 1 is 1, Fibonacci 0 is, yeah, what am I saying? Yeah, you get the idea. Why am I having so much trouble? Times phi plus Fibonacci n minus 1 for the constant coefficient. So now we have a relationship between powers of the golden ratio and the Fibonacci sequence. Okay, so I thought that was interesting, and it may come up in your mathematical career. Okay, so I think this has been a long enough section, so I'm going to let you go, and I'll see you in the next section.